a massive production line suddenly halts. Red alarms trigger across the control room. An entire processing facility grinds to a dead stop. A single 30-pound component triggered this total operational paralysis. Maintenance teams immediately scramble to locate a replacement part and force the system back online. In the rush to restore operations, a critical engineering error occurs. They pull the exact same part number from the shelf and install a seal with the identical material specification. This blind spot is driven by a dangerous industry misconception: the assumption that all fluoroelastomer rubbers offer a universal level of chemical protection. The financial penalty for this assumption is enduring repetitive 50,000-pound downtime events that simply did not have to happen. To permanently break this cycle of failure, you have to look past the catalog part number and understand the exact molecular chemistry of what you are buying. To locate the flaw, we have to scale down from the plant floor to the microscopic architecture of a legacy fluoroelastomer. Every industrial rubber relies on a carbon backbone, a continuous structural core required to hold the material together. Looking at this model of a standard fluoroelastomer, you can see the critical flaw. Numerous bonding sites along the carbon chain are occupied by exposed hydrogen atoms. In severe chemical environments, these hydrogen positions act as highly reactive gateways. When aggressive industrial media enters the system, it specifically targets and violently interacts with these precise hydrogen bonding sites. The chemical attack severs the hydrogen bonds, physically fracturing the integrity of the carbon chain itself. This microscopic structural damage explains exactly why seals visibly swell, harden, and ultimately leak on the production line. As long as hydrogen exists anywhere on that carbon chain, the entire operational system carries a chemical vulnerability. The definitive structural cure to this vulnerability is engineered into a specific specification, FFKM. The first two letters, FF, stand for perfluoro, signaling a radical molecular shift. The engineering mechanism here requires systematically stripping away every single exposed hydrogen atom from the backbone. In their place, highly stable fluorine atoms flood the vacant bonding sites. This process is uncompromising. Not some, not most. Every single position where hydrogen would otherwise sit is occupied by fluorine. The result is an impenetrable, fully saturated chemical shield completely encapsulating the carbon core. Fluorine's strong electronegativity naturally deflects and neutralizes aggressive chemical media before it can ever reach the carbon backbone. By systematically removing the hydrogen vector, the material is engineered to be virtually immune to chemical attack. Chemical survival addresses only half the operational requirement. The material must perform mechanically, which brings us to the letter K. K stands for Kautschuk, the ISO standard term dictating true rubber behavior in industrial components. To maintain a tight seal, the material must physically compress under extreme mechanical load and instantly recover its original shape. Pure PTFE offers extreme chemical resistance, but it lacks physical memory entirely. Under pressure, pure PTFE deforms permanently, rendering it useless in a dynamic sealing environment. FFKM resolves this conflict. It secures the indestructible chemical resistance of PTFE without sacrificing true elastomeric sealing capability. By combining these properties into one material, engineers no longer have to choose between chemical survival and physical sealing integrity. The final structural letter in the specification is M, representing the methylene backbone. This fully saturated carbon chain provides the foundational thermal stability required to operate in extreme environments. Its structure allows for continuous, unbroken operation at 200 degrees Celsius. It can survive violent temperature spikes up to 300 degrees without hardening or breaking down. It repels highly aggressive media, sour gas, raw steam, and corrosive amines without swelling. And it easily withstands the highly aggressive, repetitive, clean-in-place cycles that routinely destroy standard rubbers. For the plant engineer, this molecular perfection translates to permanently eliminating constant chemical compatibility checks from their daily workflow. Specifying FFKM converts a highly unpredictable point of failure into a permanently stable operational node. Shifting this specification from the engineering floor to the procurement department introduces new, different metrics. Looking at this cost breakdown, the initial friction point is obvious: the noticeably higher upfront unit cost of an FFKM seal compared to legacy components. But the true cost of a standard seal quickly eclipses that base price when you factor in continuous monthly reorder cycles. To that, you add the highly inflated costs of emergency inventory stocking and overnight rush delivery fees. Finally, you factor in the hidden labor costs associated with constantly dispatching maintenance crews for repetitive, identical repair interventions. Specifying FFKM completely flattens this cumulative cost curve because a single purchase permanently solves the application. This creates strategic value through radical vendor consolidation and the maintenance of a predictable, slow-moving inventory. Defending a higher initial spend on FFKM mathematically guarantees a vastly lower total cost of ownership. At the enterprise management level, the perspective shifts from line item costs to total operational security. At this massive operational scale, the FFKM seal functions as much more than a component. It acts as a structural enterprise risk mitigation tool. The material prevents the escape of toxic media, which eliminates the primary source of environmental violations and subsequent regulatory shutdown orders. It also provides the ultimate financial protection by preventing the massive operational revenue loss caused by completely halted production lines. This logic informs the core diagnostic philosophy developed over decades of problem-solving at Acumen Seals. As Andrew Sykes states, if your seals are continuously failing and nobody is questioning the material specification, that is exactly where you start. Deeply understanding the FFKM molecular structure is the only absolute way to defend the spend, protect the plant, and eliminate unnecessary operational risk.